Okay. Once again, today's class is extremely important because we are going to talk about the dynamics of the robot. In the last class, our assumption was that we had lumped mass. What do I mean by lumped mass? Lumped mass assumption means that the total mass of the robot, either the robot joint or the robot link, is located at one point. For an example, in last class, we looked at a, a robot which was approximated something like this, wherein we have the mass, we have the link length L, but the link itself was massless, which means if I were to draw the kinematic diagram of this robot, this kinematic diagram of the robot would look something like this. There is this mass at the end. There is no mass of the link. In today's class, we are going to relax this assumption and we are going to look at the case when the mass is distributed. So imagine that you have a robot wherein you have the revolute joint, you have the motor, and then there is this mass that is distributed. If you look at all the practical robots, typically you will never have a case where the mass of the robot is concentrated at one location. Now, please understand, whenever you have a case such as this, when the mass is distributed, we have a concept which is called as the mass moment of inertia. Mass moment of inertia is given as I, moment of inertia. And the mass moment of inertia is defined as the mass multiplied by the radius of gyration, m times radius of gyration square. Gyration means dancing or rotation. In this particular case, if this mass is m, if it is at distance L, the I for this system, which is the mass moment of inertia, is mass m multiplied by L square, where that is the radius at which this mass is located. So mass multiplied by the radius of gyration is ml square. We derived this problem before, but what I want to do is I want to solve this problem, the simple pendulum problem, in a slightly different fashion. So I'm looking at this pendulum problem, and for this pendulum problem, I want to find out the kinetic energy of rotation. Kinetic energy of rotation is given as 1/2, where I is the mass moment of inertia multiplied by the angular velocity square. So 1/2 I theta dot square. Then I would find out the potential energy. The potential energy is measured from the datum. If this angle is theta, this is going to be mgl cosine of theta. Since this is the datum, the mass is below the datum, this potential energy is mgl cosine theta. So no, MGL sine theta, my apologies. This is MGL sine theta. If this is theta, sorry, this is theta, then this is gonna be cosine theta. Sorry, this is cosine theta. MGL cosine theta. Now I want to find out the Lagrangian L, which is T minus V, where T is the kinetic energy, which is 1/2 I theta dot square minus I have this potential energy, which is minus of MGL cosine theta. So I have this Lagrangian, which is 1/2 I theta dot square plus MGL cosine theta. And I want to find out the differential equation of motion using the Lagrangian formulation, partial L by partial theta dot d by dt minus partial L by partial theta is equal to 0. Now partial L by partial theta dot, which means theta is a constant. This gives me an expression d by dt I theta dot minus, the first term is going to be constant. Cosine theta becomes minus sine theta. So you're going to have minus MGL sine theta is equal to 0. And we derived the same expression in last class. The only difference there is we use the translational kinetic energy. In this particular case, we are using the rotational kinetic energy. And then this equation becomes I theta double dot plus M times G times L sine theta is equal to 0. And I is mass M multiplied by the radius of gyration square theta double dot plus MGL sine theta is equal to 0. So at the end, I get this expression theta double dot plus G over L sine theta is equal to 0. And this is the same equation that we derived in the previous class. Now, what is the difference here? Now, please understand the difference, only difference here is I'm using the kinetic energy of rotation. Kinetic energy of rotation is given by 1/2 I theta dot square. So please understand, kinetic energy of translation is given as 1/2 mv square. Kinetic energy of rotation is given as 1/2 I omega square, where omega is the rotational velocity and I is the mass moment of inertia. What is a mass moment of inertia? Mass moment of inertia is nothing but the inertial effects given because the mass is allowed to rotate about a point. So that is called as mass moment of inertia. Now, let me solve a very simple problem wherein if I have a slender rod, which means I have this rod, the length of the rod is L, and the mass of the rod is M. Mass is equal to M. This whole mass is distributed across the length. And let's try to find out the mass moment of inertia. So I'm going to find out the mass moment of inertia about, if this is x-axis, this is y-axis, I'm going to find out mass moment of inertia about z-axis. I am interested in finding out the mass moment of inertia about z-axis. Since this mass is distributed over length of L, so mass per unit length is equal to m by L. Mass per unit length is m by L. Mass moment of inertia, which is the value of I, is given as mass multiplied by the radius of gyration square. And I'm gonna, since this is a symmetric rod, this distance, I'm gonna take this as my datum. This is going to be L by 2. This is going to be L by 2. So my mass, since it is distributed, I'm gonna find out this small strip, and this strip, the thickness of this strip is dr. This strip is at distance r. So I would find out the mass of this small strip. Mass of this small strip is m by L multiplied by dr. This strip is at distance r. So the radius is r. So radius square is r square. And I need to integrate this whole thing from minus L by 2 to plus L by 2. So I have m over L r square dr. Now m and L comes out of the integral sign. R square, the integral becomes r cube by 3. And then I have L by 2 minus L by 2. So this expression becomes m divided by L. 1 by 3 comes out. And then here it's gonna become L by 2 cube minus L by 2 cube. So this becomes 2L by 8. So m divided by 6 multiplied by 2L by 8. So no, L cube. So this becomes 2L by 8. 2L by 8. I'm missing one term. L by 8, and this becomes, this is 1 by, yeah, this is 3. This is 1 by 3 L 2 L by 8. And then this becomes m L square by 12. So mass moment of inertia of a slender rod about Z, IZZ, is m L square by 12. Now this is an important expression. Now, if in this problem, what we are assuming is, we are assuming the thickness of this slender rod is very small compared to L. Now what I want to do is, I want to take a bar which does not have this assumption. So the length, width, and height. So let me show this to you. So I'm going to call this as V, this X, and this Y. This thickness is T, this width is W, and this length is L. Now understand, this is the slender rod, which means the mass is distributed across the length. So mass of this whole thing, mass is equal to M. This slender rod or this bar can have mass moment of inertia about x. So it can have mass moment of inertia about x, which is called as Ixx. It can have mass moment of inertia about y, which is called Iyy. It can have mass moment of inertia about z, which is called Izz. It can have Ixx, it can have Iyy, it can have Izz. I want you to remember this expression, mass moment of inertia about x-axis. Now, about x-axis is this. Now, so physically, what is the physical interpretation of this mass moment of inertia? Inertia means laziness, how lazy one is. So inertia means flow, laziness. Higher mass moment of inertia means it takes more effort, it takes more torque to get that thing into motion. So Ixx, large Ixx means it is difficult to rotate that rod or that bar about the x-axis if its Ixx is larger. Ixx for this guy is given as M. Since it is about x, you would say y square plus z square divided by 12. So what you do is, now my here the mass is M. Find out the length about the y. The length about the y-axis is given as L square. Length about the z-axis is given as T. So the mass moment of inertia of this rod about xx is ml square, m in the parentheses L square plus T square by 12. Iyy is m divided by 12. Now please understand, since the moment of inertia was about x, which means how hard it is to rotate that slab around x, you had y square and z square. If the moment of inertia is about yy, you would have x square plus z square. So you would have x square plus z square. And here you will write m by 12. X dimension is w square. Z dimension is t square. And for z, which is m by 12, x square plus y square, which is m by 12. Now x is L square and y, no, x is w square, and y is L square. So these are the mass moment of inertia about Ixx, about Iyy, and about Izz. Now, looking at this, one important thing to note is mass moment of inertia depends where you are taking the moment. In this case, the mass moment of inertia is about the CG. Mass moment of inertia is about the CG. So if I were to write the inertia tensor, now please try to understand, mass moment of inertia is actually a 3x3 matrix. Mass moment of inertia is about a 3x3 matrix. Whenever you are finding out the mass moment of inertia about the centroid, that inertia tensor, which is called as I, is a diagonal matrix, and you get Ixx, Iyy, and Izz. And you have zeros over here and zeros over here. So for simplicity, mass moment of inertias are always taken at the centroid of the object. Centroid is the point where that whole object can be balanced, which means all the forces, unbalanced forces, they cancel each other. Now, the question comes is what happens when this object or a robot is not hinged at the center. And now this is an important problem that I want to solve. Imagine that you have a robot. You have a robot, and this robot is a slender rod, and that robot is hinged at one end. This robot is hinged at one end. Length of the link is L. Mass is distributed, that is M. And if I want to draw this robot, the kinematic diagram of this robot is gonna look something like this. Kinematic diagram of this robot is gonna look something like this. Now, how do you solve this problem? First and foremost, understand that this link has the centroid somewhere over here. So you have the centroid over here. So mass of the slender rod can be considered to be fixed at that point, which is at the center. And then if you want to find out the value of the kinetic energy, you are going to have two types of kinetic energies. One kinetic energy, so if I want to solve this problem, there will be kinetic energy of translation and there will be kinetic energy of rotation. So kinetic energy of translation is this mass moving maybe in this angle, this direction, this theta. So I would have kinetic energy of translation is the velocity of this mass Vm. I would call 1/2 m Vm square. And then kinetic energy of rotation is going to have 1/2 I omega square. Now please understand 1/2 m Vm is nothing but theta dot multiplied by L by 2, because omega times r, velocity is omega times r. And this distance, this radius is L by 2. So omega times r, theta dot L by 2 square is the kinetic energy of translation. Kinetic energy of rotation is going to be 1/2 m L square by 12 theta dot square. So the total kinetic energy in this case, total kinetic energy is going to be 1/2 m theta dot square L square by 4 plus 1/2 m L square by 12 theta dot square. Now this expression can be rewritten as 1/2 m in the parentheses L square by 4 plus L square by 12 theta dot square. Now this expression can be written as 1/2 m L by 4 L by 12 which is 3 4 L by 12 which is L square by 3 theta dot square. So this expression is going to be 1/2 m L square by 3 theta dot square. And I want to spend some time just to talk about what I have done here. Yeah.
How did you substitute M theta dot A?
Correct. I would explain this once again because this part is very important. Now imagine most of the times you will have the robots where the mass is distributed. How do we solve a distributed mass problem? If the mass is distributed and the hinge or the robot is pinned at anywhere else than the center of gravity, what you do is you basically add the mass at the center of the gravity. So for an example, you have this slender rod where the entire mass is distributed across the length of this rod. The whole mass is located at the centroid shown as the black dot. That is where the mass is located. Now here, there are two types of kinetic energies. One is the kinetic energy of translation. The other one is the kinetic energy of rotation. Where is this kinetic energy of translation is coming in the picture? Kinetic energy of translation is coming in the picture because that mass which is located at the centroid has some velocity that is shown by Vm. What is that velocity? That velocity is omega, which is the angular velocity, multiplied by r, which is the radius at which that mass is located. So omega times r is the velocity of that mass. So the translational kinetic energy is going to be 1/2 m, which is the mass, Vm square. Everyone understood this translational kinetic energy? Since the mass is distributed across the length, it will also have the rotational kinetic energy. And rotational kinetic energy is given by 1/2 I times omega square. Yeah.
So can't we just take the I from the pinned the edge and you will directly get this thing?
Correct.
You
That
don't
is
need to-
absolutely possible. But you can only do that when it's a slender rod. Imagine if I were to give you a robot that is a very complicated shape, then you won't be able to find out the I because the mass will be distributed. So bear with me. But you're right. You can actually combine all that and just use ml square by 3 and solve the problem. But what I'm trying to do here is there are two types of kinetic energy. One is the kinetic energy of translation, other one is the kinetic energy of rotation. I found out the kinetic energy of translation, which gives you the mass multiplied by the translational velocity of the mass square. Kinetic energy of the rotation is the mass moment of inertia multiplied by the angular velocity square. At the end, when you combine all that, you get one expression for the kinetic energy, the total kinetic energy. And that total kinetic energy expression you have to use when you solve Lagrangian. Everyone understood this? Yeah.
Added both of them.
I added both of those because please note the first part is theta dot L by 2, square it. So theta dot square L square by 4, and you have L square by 12 theta dot square. So you have 1/2 m theta dot square common. Yeah, and then basically you added L square by 4 plus L square by 12, and that gives you L square by 3. Now I found the kinetic energy of rotation. Now I want to find out the potential energy. Whenever I'm solving the potential energy, since this mass is distributed, I'm approximating the distributed mass to be located at this point, So my potential energy is going to be the distance. This would be the distance because the mass will be located at the centroid of this rod. And this distance is going to be L by 2 cosine theta. So potential energy is going to be minus m g L by 2 cosine theta. So now if I want to form the Lagrangian, my Lagrangian will be T minus V, which is 1/2 m L square by 3 theta dot square plus m g L by 2 cosine theta. And I can use the MATLAB, or I can use the Lagrangian equations to solve this problem. Everyone understood this? So what is the key takeaway here? Key takeaway here is, if you have the block type of system, which is like a discrete system where the link does not have any mass, all the mass is located or lumped at the end, you can solve using either the kinetic energy of rotation or kinetic energy of translation. That will give you the answer. But whenever the mass is distributed, then you have to use kinetic energy of translation and kinetic energy of rotation to find out the total kinetic energy. Everyone understood this? So in real robots, what's going to happen is you are going to have the system where the mass is distributed. And at that time, you have to use this type of analysis to solve the problem. Now I'm going to work out a problem, and then I will show you. You can go to MATLAB and then you can solve the problem. Before I start solving the problem, here are a couple of key takeaways. How do you solve a dynamics problem? In the dynamics problem, first and foremost, you have to solve the forward kinematics problem, which means solve forward kinematics problem. Second, find the position of each mass and its centroid. Find position of masses. Then next thing, find the velocity of masses. So this will come from the homogeneous transformation. Find velocity of masses. Once you find the velocity of the masses, you can find out the kinetic energy of translation. KET stands for kinetic energy of translation. Then you can find out the angular velocity of the masses. So theta of mass, theta dot of masses. Once you find the angular velocities, you can find out the kinetic energy of rotation. Once you find out the kinetic energy of translation, once you find out the kinetic energy of rotation, you can find out the total kinetic energy, which is kinetic energy of translation plus kinetic energy of rotation. Then find out the potential energy. Find potential energy. Then which is V. And next step, find Lagrangian, which is T minus V, and then you can use MATLAB. So in this particular case, what you need to do is whenever you have the distributed mass, you can solve the forward kinematics problem, find the position of the masses, find the velocity of the masses, then find out the angular velocity of the masses, find the potential energy, and then finally find the Lagrangian. Now, I'm going to work out the problem. So everyone, please pay attention. So to set up the problem, we have solved similar problem in last class. This problem is I have R parallel R joint. So you have, this is the first revolute joint, this is the second revolute joint, and then we have the end effector over here. In last class, we solved the problem where all the mass was located at the end effector. Now in today's class, I'm going to make this problem a little bit more complex, and we are going to have the mass distributed here, and we are going to have this mass distributed over here. So which means I have this link and I have another link, and this link has mass m1, which is distributed. I have this link which has mass m2, which is distributed. Everyone understood this? So if you look at the top view, you would notice that this problem would look something like, you have the first link, and then you have the second link, which is shown over here. So this link has mass m1, this link has mass m2, and this angle is theta 1, and this angle is theta 2. What is the difference between this problem and the previous problem? In the previous problem, this link was massless. This link was massless. The total mass was focused or located at the end effector. In this problem, the mass is distributed. Whenever you solve the robot problem, typically all the robot problems would be like this, where the mass will be distributed. Now, how do we solve this problem? First and foremost, to solve this problem, we have to solve the forward kinematics problem. The forward kinematics problem is same as you will assign the coordinate systems, and we have solved this problem multiple times. You will assign the coordinate systems, find out 0 h1, find out 1 h2, and you can find out at the end 0 h2 is equal to 0 h1 plus 1 h2. And let me quickly write these matrices. These matrices gonna be cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1, 0, 0, 0, and then this is going to be A1, 0, 0, A1, 1. And then what you have is we have to find out 1h2. So 1h2 is again, so this is gonna be L1 and this is gonna be L2. So cosine, actually this is gonna be L1 cosine theta 1, L1 sine theta 1. I will write this down. Theta 1, this will become L1 theta 2 cosine theta 2 minus sine theta 2 sine theta 2 cosine theta 2 0 0 0 0 1 0 0 0, and at the end you'll have uh, so I'm making a mistake here. Let me see. Uh, this is one. Oh, this is gonna become L1 cosine theta 1, L1 sine theta 1, A1 1. This is gonna be L2 cosine theta 2, L2 sine theta 2, and this distance is gonna be E2 and 1. And then you will solve this and get the equation for the forward kinematics, which is gonna be 0h2, which is 0h1 multiplied by 1h2. Okay, now the question here is, if you look at 0h1, this term here is showing you the distance between the 0th frame and the first frame. But please note, since this is the slender rod, the mass is located somewhere over here. The mass is located somewhere over here. So M1 is located at the centroid of the first link. So for mass M1, Px is going to be L1, which is the length of the link, L1 by 2 cosine theta 1, because the mass is located at the half of the link length. Py is going to be L1 by 2 sine theta 1. Pz is going to be A1. Now please understand, if you look at 0h1, the last column, that is going to give you the x distance between the 0th frame and the first frame, y distance between the 0th frame and the first frame, and the z distance between the 0th frame and the first frame. If you look at 1h2, that is going to give you the distance between the first frame and the second frame in x, about x1. Second, if you look at L2 sine theta 2, that is going to give you the distance between the first frame and the second frame in y direction. And the last one is going to give you the z distance between the first frame and the second frame. But for mass M1, that is located at the centroid of the link. So I have L1 by 2, L2 by 2, and A1. Similarly, for mass M2, I need to find out, silence please, for mass M2, I need to find out Px, Py, and Pz. And if you recollect from the notes that we discussed in last class, this distance is going to be L1 cosine theta 1 plus L2 by 2 cosine theta 1 plus theta 2. L1 sine theta 1 plus L1 by 2 sine theta 1 plus theta 2. And Pz is going to be E2. Once again, question? So once again, I want to explain this. Oh, A1 plus A2, correct. A1 plus A2. So the mass is located at this point. This mass is located at this point. I want you to find out this x distance, this y distance. X distance is L1 cosine theta 1. This distance is L1 by 2 cosine theta 1. The y distance is L1 by 2 sine theta 1. This distance is this total distance, which is L1 cosine theta 1 plus L2 by 2 cosine theta 1 plus theta 2. This distance is L1 sine theta 1 plus L2 by 2 sine theta 1 plus theta 2. What is the difference between these distances and the previous problem? In the previous problem, the mass was located at the end. So you had just one mass that was located where the rotation joint of the frame is. Second mass was located at the end effector. Here, the mass is distributed. Everyone understood this? Okay. You have the Px, Py, Pz. You can differentiate these and you can find out Px dot, you can find out Py dot, you can find out Pz dot. You can find Px dot, you can find Py dot, you can find Pz dot. These are for masses M1, M1, M1. You can use this information to find out the translational kinetic energy. So kinetic energy of translation is going to be 1/2 M1 Px M1 dot square plus Py M1 dot square plus Pz M1 dot square. That is the kinetic energy of translation for the first mass. Similarly, you can find out Px dot M2 by taking the derivative of this. You can find Py dot M2 and you can find Pz dot M2. And you can find out the kinetic energy of translation for the second mass, which is 1/2 M2 Px M2 dot square plus Py dot square M2 plus P dot square Z M2. So now you have the kinetic energy of translation for the first mass, kinetic energy of the translation for the second mass. This is similar to the previous problem. The only difference here is since it's a distributed link, the mass is located at half of the link distance. Everyone understood this? So the distances Px, Py, Pz were actually half of the link length. But important part is, in this problem, since it's a slender rod, we have to find out the kinetic energy of rotation as well. So we need to find out the kinetic energy of rotation. So this gives me the kinetic energy of translation. To find kinetic energy of rotation, we need to find out angular velocity of the first link. We have to find out the angular velocity of first link. Angular velocity of the first link is given as omega x, omega y, omega z is equal to the first rotation matrix, which is 0, r0 and 0, 0, theta 1 dot. 0, r0 is the identity matrix, so which is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1 multiplied by 0, 0, theta 1 dot. So the angular velocity of the first link is omega x, omega y, omega z. Omega x is going to be 0, omega y is going to be 0, omega z is going to be theta 1 dot. Now what does this mean? I want you to look at the robot configuration. And we solved this in the previous class. Z naught is the z direction that is going up. If you look at the robot, that link number 1, is that link number 1 rotating about x? Is that link 1 rotating about y? Or is that link 1 only rotating about z? Link 1 is only rotating about z. So when I look at the angular velocity of that link, I observe omega x, the rotation about the link, the rotation about x, the velocity about x is 0, velocity about y is 0, but velocity about z is theta 1 dot. Everyone understood this? So the angular velocity of the first link is theta 1 dot. Kinetic energy is 1/2 I ZZ of link 1 theta 1 dot square. Now IZZ 1 is 1/2 M L1 square by 12 theta 1 dot square. So we found out the kinetic energy of rotation for the first link. Now I need to find out kinetic energy of rotation for the second link. To find the kinetic energy of rotation about the second link, I need to find out angular velocity of second link. Now, angular velocity of the second link, I'm going to write this down. Omega x, omega y, omega z is equal to 0 r0. The angular velocity of the first link, 0, 0, theta 1 dot, plus the rotation matrix 0 r 0 r1, 0, 0, theta 2 dot. Now it's extremely important to understand what this is. Now this is the angular velocity of the first link in its body coordinate system. You are transferring this body coordinate system, angular velocity of the first link in the body coordinate system into the inertial coordinate system by multiplying with the rotation matrix. But since for the first link, the body coordinate system and inertial coordinate system is one and the same, you get an identity matrix. That is indication of 0 r0. This stuff is a little tricky, so please pay attention. Now this is for the second link. Angular velocity of the second link is nothing but 0, 0, theta 2 dot. 0, 0, theta 2 dot. Now this is the angular velocity of that link, but we need to convert the body angular velocity into the inertial or the fixed rate in a angular velocity. So I need to transform the rotation matrix. So 0 R1. So when I use this rotation matrix, the body angular velocity gets converted into the inertial angular velocity. So this expression, and I want you to understand 1 0 0 0 1 0 0 0 1 0 0 theta 1 dot. This silence, please. This is gonna become cosine theta 1 minus sine theta 1 0 sine theta 1 cosine theta 1 0 0 0 1 and you have 0 0 theta 2 dot. Now when you perform all this multiplication, you would realize omega x is equal to 0, omega y is equal to 0, and omega z is equal to theta 1 dot plus theta 2 dot. Now what does that mean? We derive the same expression. So you have one link. This is link number 1. You have link number 2. And both these links are rotating about z. Angular velocity of the first link is nothing but theta 1 dot. That's what you got. Angular velocity of the first link about the z-axis is theta 1 dot. But the angular velocity of the second link is nothing but angular velocity of the second link about its own axis, theta 2 dot plus theta 1 dot. What that means is here, check this out. If the angular velocity of this guy is theta 1 dot, if the angular velocity of this guy is theta 2 dot, the total angular velocity of the second link is going to be theta 1 dot plus theta 2 dot. Everyone understood this?
Wouldn't it be given by the distance from the
No, angular velocity of a body will be same anywhere on the body. Translational velocity of the body will be different. Example, if you have this body, if you measure the angular velocity here, it's gonna be omega. If you measure angular velocity over here, it's gonna be omega. But if you measure the translational velocity here, it's going to be VA. If you measure the translational velocity over here, it would be VB. Translational velocities are angular velocities multiplied by the radius. Angular velocity of the body anywhere, it would be the same. Any questions? Yeah. Yeah, so what needs to happen is, in this particular case, the problem is little simple because that link was rotating only about z. But what may happen is you can have a case where the link could be rotating about z, could be rotating about x, could be rotating about y. And you can have angular velocities in x, angular velocity in y, angular velocity in z. At the end of the day, yeah. Oh, no, theta, just no, not square. Theta 1 dot plus theta 2 dot. That is the total angular velocity of the link 2. And think about it like this, that if angular velocity of the link 1 is 0, the angular velocity of link 2 is just theta 2 dot. But since the angular velocity of link 1 is theta 1 dot, angular velocity of link 2 is theta 2 dot, you have the total angular velocity of the link 2 is theta 1 dot plus theta 2 dot. This stuff may seem complex, but at the end of the day, here is what we are going to do. At the end of the day, somehow we have to find out the Lagrangian. What is the Lagrangian? Lagrangian is the kinetic energy minus potential energy. What are the two types of kinetic energies? There is the kinetic energy of translation and there is kinetic energy of rotation. So you have this complicated robot and I worked out this problem by hand, but most of the times we use some type of a software to solve this problem. So when you are going to solve the actual dynamics problem, very rarely you will go through the mathematical steps that I have shown over here. You would use some type of a computer algebra to do all this. So what is going to happen? You are going to find out where the mass is distributed, then find out the center of gravity of that distributed mass, and you are going to assume that mass is lumped at the center of gravity. You are going to find out the kinetic energy of translation for that mass. You are going to find out the kinetic energy of the rotation of that mass, and you are going to repeat that for that big robot. If your robot has maybe 3 links, if your robot has 4 links, if your robot has 5 links, what you are going to do is you are going to find out kinetic energy of translation for each link, kinetic energy of rotation for each link, and then you will sum all the kinetic energies. So whatever we have done here, so we have kinetic energy of rotation for the second link, which is 1/2 I ZZ2. Since the total energy is theta 1 dot plus theta 2 dot square, and this is going to be 1/2 M L2 square by 12 theta 1 dot plus theta 2 dot square. So you have two kinetic energies of translation and you have two kinetic energies of rotation. So total kinetic energy is the kinetic energy of translation plus kinetic energy of rotation. That gives you the total kinetic energy. So you are going to have kinetic energy of translation for mass M1. You are going to have kinetic energy of rotation, kinetic energy of translation for mass M2. You would have kinetic energy of rotation for mass M1, kinetic energy of rotation for mass M2, and then you are going to have a potential energy. Now, in this case, since this robot is in the horizontal plane, you can see the kinetic energy is different, but the potential energy is going to be the same. So potential energy is going to be M1 G A1 plus M2 G A1 plus A2. Are you with me so far? This looks complex, but what you need to do is you need to follow this systematic recipe we talked about: forward kinematics, then velocity of the masses. Then you have to find out the angular velocity of the masses. You have to find out the potential energies, find out kinetic energies, and then use the Lagrangian approach. And once all this is done, the last step is you have T and you have V. So L is equal to T minus V. And then once you find out the Lagrangian, you can use MATLAB. And you can use MATLAB and solve the problem. Now, you would appreciate that for a simple 2 degree of freedom robot, this problem becomes quite complex. And in here, your first revolute joint and the second revolute joint were parallel to each other, which means you did not have angular velocity components in X or Y. When you have a robot, which is R perpendicular R, maybe parallel R, a manipulator configuration or a spherical wrist configuration, you have to follow the same approach. But the beauty of this approach is, since it does not depend upon any vector algebra, all the quantities are scalar quantities, whole thing can be programmed inside a computational software like MATLAB very easily. Everyone understood this? And that is the way we typically solve this problem. What I want to do is I want to use MATLAB. Actually, I want to use MATLAB and solve kind of, let me see, I have 5 minutes. I want to solve this.
You solve it for parallel conjugate. What if it was perpendicular?
Yeah, if it is perpendicular, the problem is straight. First, you have to solve the forward kinematics problem. Once you solve the forward kinematics problem, you have to find out the position of each mass, Px, Py, Pz for mass m1, Px, Py, Pz for mass m2. Find out the translational kinetic energy for mass m1, translational kinetic energy for mass m2, and solve that problem. And as a matter of fact, if you look at this robot dynamics, I have solved this problem where R90R, which is robot with a slender rod. So this problem, if you look at this problem, wherein you have the first revolute joint and the second revolute joint is perpendicular to the first revolute joint. If you look at our robot dynamics, this is our robot dynamics. I want to show you what changes that you will make. So this is nothing but the kinetic energy of translation. So kinetic energy of translation, clearly I'm going to have the kinetic energy of translation for the first mass. So I'm going to call this T1m. This is the kinetic energy of translation for first mass. This first mass is located at the distance, this first mass is located at the distance L1 by 2. So I will write this by 2. This term here will be again L1 by 2. Now the second mass, please note, you are going to have the first length L1 sine theta 1 theta 2. This is going to become L2 by 2 theta 1 theta 2, and then this is going to become L1 L2 by 2, and then here your L1 term will remain as is and your L2 term will become half. This is the kinetic energy of translation for the second mass, M2. Kinetic energy for rotation, T1, so I'm going to call here T2R, T2 underscore R, 1, so T2 underscore R2 is the kinetic energy of rotation for mass 2. Kinetic energy of translation for mass M1, kinetic energy of rotation for mass M1. So at R1, okay. R1 is going to be 1 by 12 multiplied by M1 multiplied by L1 square. Kinetic energy of rotation for the second mass is going to be 1 by 12 multiplied by M2 multiplied by theta 1d, th1d plus th2d square. No. And here it's gonna be th1 d. Just 1 second. th2 1 by 12 m2 L2 square multiplied by th1d plus th2d, th1d, yes, th1d, correct, th2d, and then here, and then V1 is going to be M1G A1, V2 is M1G A2 plus A1. Once again, I want you to quickly look at my code. So first, this is the kinetic energy of translation. Kinetic energy of translation is mass, which is a distance L1 by 2, theta 1 d square, and then M1 L1 by 2, theta 1 d square. Then I have the kinetic energy of rotation, and then I have the kinetic energy of translation for the second mass, and I have the kinetic energy of rotation for the second mass. And once that is done, you click run. Oh yeah, I made a mistake here because I need to change T2 underscore M2 plus T2 underscore R2 plus T1 underscore M1 plus T2 underscore correct, T1 underscore R1.
Change
Line
line 13.
13. T2 M2, T2 R2. Yeah, T1. Yeah, this is correct, right? T1 R1, T1 M1, T2 R2, and T2 M2.
So at the end of 13th line, you need to put.
What? Semicolon?
Yeah.
Good. And then the code would run, and then it will give you the plots. So you have to modify the code to get the answers. And then you are gonna get these, yeah,
How many lengths is our assignment gonna be?
lengths.
Yeah, how many, like, how, complicated is the robot in our assignment?
Yeah, as you can see, this robot only had 2 links.
Right.
Still, it took so much time. But the idea is once you understand this concept, this whole thing can be coded. So when you are going to solve an actual robot, I don't expect you for a very complicated robot for you to derive the Lagrangian expressions. But I want you to know how that process is implemented. But we will use some type of a MATLAB software. We'll use a MATLAB code to solve the robot dynamics and controls. And then this is what you see. Yeah.
For finding the angular velocity, we just introduce rotation.
Yeah. So you have for each link, for each mass, you have to find out the translational kinetic energy, rotational kinetic energy. Translational kinetic energy, rotation kinetic energy. You have to do that for the entire over the entire length of the robot.
If I have another I will do it next, but I had like 1 hour.
Yeah, then what you need to do is you need